Here we're going to talk about fragmentation in mass spectrometry, just the very basics of it. It's really complicated, and fragmentation can include chemical reactions like eliminations. There's quite a lot to it, but this is just what we need to get us started here. So our molecule, I just chose isomeric pentane here, and that'll just represent our basic molecule. I've redrawn it here to show all the bonds. Really, these two structures are the same, just abbreviating by not writing in all the hydrogens there. All right, so here's our molecule again, and then here's our molecular ion. All right, so after that molecule gets ionized, and we'll look at how things fragment and what the lines on the spectrum mean, really, at that rate. So um, our molecule here has a molecular weight of 72, right? That's shortened, it's like 72.15. We'll just stick with the basic numbers so we can keep track. And you can look up molecular weights. Of course, also a nice, easy way to do it for hydrocarbons is, carbon's 12, hydrogen's 1, right? So if we've got C5, H12, right? That should add up to 72 for 12 for every carbon and 1 for every hydrogen, right? If I've done some math incorrectly, put it in the comments if you're in my class. Actually, extra credit for pointing out mistakes. So 72, if we strip an electron away, right? So this passes through the mass spectrometer, we get our molecular ion. We've stripped away an electron. We haven't really affected the mass. The mass in mass spectrum tends to be read out as m/z. It's still going to be 72, so that's the mass of this whole particle. The electron that has been lost is pretty minimal. So drawing out the structure, missing an electron, that electron's got to come from somewhere, right? They're all bonded electrons in this hydrocarbon, and I've arbitrarily kind of chosen to put the electron here, right? So imagine all these bonds have 2 electrons. This one has gotten 1 stripped away. So all we have is 1 electron in between those 2 carbons there. So fragmentation at high temperature, high energy, that seems reasonable, right? Essentially, we're sort of breaking this molecule here. We can show that radicals use a half arrow, right? So if 1 electron goes to this carbon, this other side of the molecule hasn't really gained anything, so there's no arrows there, right? This is our fragmentation. This is where this molecule is going to break. So we get 2 pieces then, right? So the single electron went to this carbon, so we have a fragment that's going to be a radical, and then the rest, so this lost an electron gained nothing, so this other piece should have a positive charge and become a carbocation. Right, those are our 2 pieces to this molecule. Right, so it's breaking apart. This is just one fragmentation, and then the pieces we get, remember, those get separated into the mass spectrometer and separated by their mass to charge ratio, which in this case, our positive charge carbocation is going to be MC equals 43. Right? This one's going to be 29. As it turns out, only the carbocation fragments, only the positive charge fragments are the ones that are accelerated through the magnetic field and actually get detected. But it can potentially fragment both ways. So this break, the electron can sometimes go the other way, giving you the fragment at 29. Right? But this is overall what's happening, right? So we inject our molecule, it gets ionized, it comes apart into 2 fragments, right? There's lots of different bonds can break. We can have sort of infinite amounts of variation here, but the simple big fragments we get here, 3 carbon and a 2 carbon piece, they're going to show up at different ranges on the spectrum. So to start with, if we were looking at a mass spectrum, we'd expect to see a peak for the molecular ion. We'd expect to see a peak for this fragment and a variety of other fragments as well. So if we're looking at this whole molecule, any of these bonds can break, right? So if it breaks here, right, we'd expect to see a 15 mass piece, right? So carbon's 12, 13, 14, 15. Right? The carbocation for that, if it was formed, CH3+, that's one of our least stable carbocations, and that's part of the reason why on a spectrum the peak at 15 is usually really small. It's pretty unlikely compared to the other breakages, just because the carbocation stability can determine the abundance of the fragment. But thinking about it, it could break here. The break from before, resulting in these two pieces, 3 carbon, 2 carbon. This could break, right, resulting in a 1 and a 4 carbon piece. Any of these carbon-carbon bonds can. Carbon-hydrogen bonds can fragment as well. So you see not just 5 or 6 major peaks, but lots of different ones, right? Loss of one, loss of hydrogen there, loss of methyl groups, breaking into 2 and 3 carbon pieces. What we'll see from that is for a spectrum here, which I won't draw for this video, but we'll look at spectra in another video. So you see a peak of 15 from a 1 carbon piece, but then you'll also see 29, 43, 57, and then the molecular ion at 72 if nothing comes apart. All right, but say you see your molecular ion at 72, say you see a peak at 71, where might that have come from? Well, say this whole molecule stays intact except for this break here. It loses a hydrogen, right? Then you'd expect to see a peak 1 mass unit lower, right? So we're looking at a peak at 15, 2 carbons, the peak at 29, right? 3 carbons, yeah, this is getting messy. 3 carbon piece, a 4 carbon piece, right? Lots of different fragmentation possibilities are going to show up on the spectrum. Again, this is just a starting point because those fragments can degrade, they can do reactions. Different atoms, of course, will have different mass other than 12 and 1 for carbons and hydrogens, but hydrocarbons, this is what we're looking at. The molecule ionizes, it breaks apart into 2 pieces, right? And all of our possible fragmentations usually do happen. It's just then a matter of the most stable fragments, like something like this, which is a secondary carbocation, will tend to be the ones you'll see the most.